Hello, Tanya Laird here, and welcome to part 3 of lecture 9 of ENGR 231 Engineering Statics. In this part of the lecture, I want to go over some of the method and theory of the method of joints, or more specifically, analyzing trusses via the method of joints. So the method of joints is fundamentally built off of just two basic ideas. One, the assumptions baked into it are as follows. One, we treat all of the joints as point particles. All of the truss joints are point particles. Joints are point particles. And thus we only need to look at summation of forces in the x direction and summation of forces in the y direction. And of course I'm looking at this for a planar truss. If we had a three-dimensional truss or a space truss, then things would be a little bit different. Two, we are going to assume that every member in the truss is a ideal truss member. So all truss members, or all members, are ideal truss members. And as we've seen, when we have straight members connected by pin joints, with only loads applied at the joints, what that produces is a condition where, in turn, members carry only a single axial force. Only a single axial force, either tension or compression. A single force, tension, or compression. And this is what we're going to be applying when we use the method of joints. So let's go through the basic process here. Steps in the method of joints. The first will be to isolate every single joint in a truss. Every joint in a truss replacing every member with a pair of forces. So if I have a member like this with pin joints on either end, what I will do is I will replace this when I draw my exploded view of something like this. Let's say that I have member A, or joint A, and joint B. I will then replace this as follows. Usually I'll replace this with an FAB and an FAB. Like so here. FAB and FAB. Two, draw what I refer to as the exploded view of the truss. Draw the exploded view. And the exploded view should show just simple circles for the, or just simple labels for the joints. But then also labels for all of the forces and for all member forces and external reactions. And external reactions. Three, apply equilibrium at each joint. Equilibrium, and this is going to be translational equilibrium. Equations of equilibrium. A sum of forces x and a sum of forces y to each joint on the truss in order to solve for unknown forces. So apply equations of equilibrium to solve for all unknown forces. to solve for all unknown forces. And then 4, you essentially just work your way through the truss, until all desired unknowns are found. Through the truss, joint by joint, until all desired unknowns are found. Desired unknown forces and reactions are found. Now, I should mention there is one caveat to this. Often, if there are less than 3, or if there are 3 or less, or are 3 or less, or fewer, unknown external reaction forces, it can be beneficial to solve for these directly. Treating the truss as a single rigid body. Directly by treating the truss as a single rigid body. The truss as a single rigid body. So in other words, if I have a truss like this, something like this. Let's just keep it relatively simple. And maybe I'll make this a pin and this a roller here. Rather than trying to solve for the reactions, the reactions I would have would be force X here and a force Y there, and a Y force there. And rather than trying and solving for these, let's say there's a 10 kip force or something here. Rather than trying to solve for these by just joint equilibrium, moving joint by joint, often it can be beneficial to just solve for those directly, treating the entire truss as just a single rigid body by just doing a global equilibrium using balance of forces and balance of moments on that. And we'll see that in part 4 when we look at some examples of applying the method of joints. A few notes. Let's take a look at a few notes here. 1, generally it's beneficial to simply assume that all the members are in tension. This is what I usually do when I'm applying the method of joints. To simply assume that all members present are in tension. So if I have a truss here, and I'm going to divide it up into an exploded view with all the member forces, etc. Like this. Oh, actually, you know what? Maybe I don't want to show quite that many members. I want to have something that I can draw out relatively quickly. When I draw this into an exploded view and show all of the forces that are revealed, I generally just go ahead and assume that everything is in tension. So I'm going to draw all the member forces, and let's say these are joints A, B, O, C, D, E, and F. And maybe this one actually is a pin, and maybe this one is a roller. So I'll go ahead and make that a pin and this a roller. And then I'll show the unknown forces here. So I would have a CY and a CX, and then I would have an EY. Actually, that's an FY, sorry about that. And then the member forces, I would have FAB and FAB. And then I would also have, let's just go along down the line. I would have FAC and FAC. Then I would have member FCD and FCD, and etc. along the bottom chord of the truss. FDE and FDE. Then I would have FEF and FEF. And then I would have along here FBF and FBF. And you can kind of see where this is going. FBE and FBE. And FAD and FAD. And FBD, finally, and FBD. FBD. Now, as I have this drawn, this is fundamentally impossible. It is impossible for any kind of real truss for all of the members to be in tension. Although, wait, actually, maybe. There might be some weird way if I deliberately crafted a set of loads to actually put everything in a truss into tension. Although, maybe if I like put a downward force here, a downward force here, an upward force here, and an upward force here, maybe there is some weird convoluted way to force a truss to have every single member in tension, but that would be very difficult to do. In almost any kind of real loading, you're going to have a mixture of tension and compression members. If you have a truss in positive bending is when something is bending in kind of a smiley face shape like this, say from like a downward load like that. Generally, the top chord, the chord refers to the line of truss members. So member AC here, member AB, and member BF. Generally, the top chord is in compression, and the bottom chord is in tension. So this here is in almost all cases impossible, but that's still fine. Because generally what I do is I just go ahead and assume that every single member is in tension. So I assume that all members are in tension. And the really nice thing about this is if you remember, tension is positive. So effectively what I'm doing is I'm assuming every single member has a positive force in it. I'm assuming every member has a positive force in it, and then if I get a negative number, that simply means that force is compression. Then that member force is actually compression. Then that member force is actually in compression. All right, so I think that'll do it for our brief intro to the method of joints. I think that I did want to go through and do a brief write-up, just a formal introduction to it. But in video 4, which will be the really useful and interesting one, I want to go through and actually work through some examples of applying the method of joints to solving a few examples of solving for truss member forces. All right, that'll do it for now. I'll see you all soon for part 4, and as always, thank you.